All right, thank you so much. Yeah, as he mentioned, I am the chair of the Mountain Cartography Commission of the International Cartographic Association. This was where our last meeting was, in the Tatra Mountains of southern Poland, and we hope you can make our next meeting, to be determined in 2026. Yeah, lots of great colleagues on this, and this is a user study, and working with Isa at University of Warsaw, and one of their graduate students, Katarzyna, Jean Trantham, who works for the USGS, but is doing this independently, and Arzu, who many of you may know. So relief inversion is not a problem that's particular to terrain. We tend to get this inversion of relief in all sorts of things, such as on the left here, showing something that might look more chiseled in on the left-hand part of the figure, and maybe more bas relief on the right-hand side. It looks like the line network is standing out there. The next one I kind of had a little trouble with. I see the original one there. It looks like a bowl with a little mound in the middle. But the other one, sometimes it comes and goes, but just to kind of show what that's supposed to look like, I put some chips and guacamole in there. So kind of a bowl within a bowl type arrangement. The first time I saw this was in the class John Kimmerling was teaching me, and he showed this map, which is Tanaka's original illuminated contour map. And I think most people have a pretty easy idea of perceiving this as a series of volcanoes with the craters going down in the middle. But if we just rotate the map by 90 degrees, it looks much different, and probably hard to perceive, but you might kind of see relief of inversion associated with this. I heard a lot about relief inversion. The only real study I know of that's looked into this specifically has been this one by Julian Beland and Arzu. And they were looking at different directions of illumination and seeing if relief seemed to invert for people as they looked at this. So the one on the left shows lighting from the northwest, which is, of course, the default in most GIS software, including ArcGIS and QGIS. And then the one on the right is showing the same terrain with illumination from the southeast. And when we ask users about this, we would typically be asking them to perform some task, such as identifying if the line along ABC here were a valley or a ridge or something like that. For their study, they looked at a lot of different orientations of valleys and ridges, and what they found is this, right, that we're right about this northwest illumination, or at least northern illumination, that it seems to really work much better for people. And so there is an optimal in there at 337.5. That comes up in a lot of studies, it seems, just because they found that as an optimal here. And there's also a low point at 225, which is actually not from the southeast, but from the southwest. So they really did a good job of documenting that this relief inversion is a thing, right? It doesn't occur with everyone. You can see that, but we're up in the 90% mean there as far as people that are experiencing, that are able to see things correctly, and then down at 5% or so for people that are getting this relief inversion, or not able to overcome this relief inversion. This is really especially important with shaded relief maps, and I think the reason for that is because there's not a lot of other visual cues as far as what's high and what's low. So this was a different study done by Arzu and Julian, and they were looking at shaded relief maps compared to black and white satellite imagery and also color satellite imagery. And I think with the color satellite imagery, or especially with the color satellite imagery, you might be able to get some other visual cues like greener valleys or white on the top of mountains, and that's really going to help with this relief inversion effect. So their findings for this study was that, yes, indeed, that first of all, everyone does pretty poorly with this, right? There's a lot of confusion about what's up and what's down with these sorts of naturally lighted things in the northern hemisphere as far as satellite images, but also if we shade from that direction, it's not good as well. But the other thing about it that's kind of interesting is, especially the people working with shaded relief, they were pretty confident in their ability to know what was high and what was low, and they were wrong most of the time. So really important to keep in mind this end user. They're not lacking in confidence, but sometimes they're getting it wrong. This is one that's a really nice study by Nathaniel Douglas and Carolyn Fish at University of Oregon, and this is looking at beauty and realism, and you can see that realism is kind of the light purple bar there in all these figures. And once again, they were looking at, hypsometric tinting would just be colors associated with elevation, and then the hill shading. and then the land cover and the ortho imagery. What we'll be talking about in this study is closest to multi-directional in the center one there. But in all cases here, you can see that the realism, people's perception of how realistic this looks, drops as you go from ortho imagery, which is a photograph, down to land cover, which is a cartographic product, down to hypsometric tinting that it's just based on elevation. So I think we have to be especially careful if we're making shaded relief maps, because we're not giving people a lot of other visual cues. Of course, we could add other layers and all, but just in the shaded relief itself, there's not a lot of other visual cues about what's up and what's down. This was a study done by Mariana Farmakis and Lawrence Herney at ETH Zurich, and they were looking at a lot of different landforms, and they were also interested in this effect. And so you can see they were also looking at several different lighting models, including the one in the upper left, which is the clear sky lighting model that we're going to be using for this study. And these are all the same. These are all the same digital elevations. They're shaded in different ways, including texture shading, Leland's method, and some other popular methods of relief shading here. And they were also looking at different types of landforms. So a total of 9 different landforms, 3 of which are shown here, and seeing how people could what people felt was the best way to show these different landforms. So this is one example for block mountains, which was shown in the upper and in the left of the previous slide. And they were just looking at how suitable people thought the different shading methods were for different landforms. And we can see in this example here, clear sky did quite well. A lot of people found it either most suitable or rather suitable for showing those sorts of landforms. And in general, clear sky did well for 5 out of the 9 different categories. It was found most suitable by most users who did this study for these different types of landforms shown here. So getting to our current study, the aim of the study is to compare this clear sky illumination model with the classic Lambert shading, which is what you would select if you just check the hill shading box, if you do hill shading with most typical GIS programs such as QGIS or ArcGIS Pro. And our hypothesis is that the shading relief that's rendered with this clear sky model will reduce this terrain reversal effect that we're seeing with just using the default. So we're going to choose lighting directions of the high and low from this graph here, so 337.5 and 225, and so that's going to be the independent variable that we're looking at in this user study. For the data here, we're using the sample elevation model. This was something I worked on with Bernie and Daniel Huffman and Brooke and Alex and Sarah and Tom, and it's available on Tom's website if you're interested. These sample elevation models are nice if you're just trying to try out a new technique. You want to see how it compares to what a lot of other people have used, for shading, and then see what the results are. And the specific areas that we used are listed here, but there were several different areas that we were looking at. So we were trying to counterbalance the landforms that were in these data, and then also how rugged they were. That was something we controlled for. So the user study itself, the shading types were the Lambert, the classic traditional hill shading, and the clear sky model. The light direction was from the southeast and from the southwest and the northwest. And this was a between subject study design, which means that users in the study just saw one type of the shading, and then they evaluated a bunch of different maps based on that type of shading. We did control for ruggedness and orientation, so those should not be issues. And the things that we measured were the performance accuracy, whether or not they were right that they were going up or down the hill, and then also the response time, how long it took them to say what they thought it was. But then we also collected some subjective data, which was how difficult the task was for them and how confident they were that they had done the task properly by using a Likert type scale. So here's an example of a clear sky model compared, this is not part of the study, but a clear sky model compared to a traditional sky model. They look somewhat different. You can see that, that the clear sky model does use shadowing. The one on the left also uses shadowing, but only from one direction. And the kind of the combination. So the clear sky is just sampling a sky on a clear day, the light would still be from the northwest, but there would be light distributed throughout the entire sky. So that's kind of what's creating that soft shadow effect that you're seeing. But sometimes when people ask, me what is better or worse about this type of shading, it's hard to put into words, So I think that relevant to this study, the shadows are included. I think that's important. The tones vary across flat area. This is not something we typically get with shaded relief. But also this idea of, if you look in this, it's a different lighting model, but in the lower part of this slide here, the overcast lighting, that's downtown Houston, Texas. And we can kind of see that high rooftops are lighter because you would be able to see more of that sky, more of the light from the sky would be able to get to you at the highest elevations or the highest rooftops. And kind of related to that, the deeper as you go down into street level or as you go into the crater at the top of Wizard Island there in Crater Lake, it would just get darker and darker. So lows tend to be dark, highs tend to be light, and I think this might help people with these types of interpretations. Oops, sorry. So here would be an example here showing the four different types of displays they might see. The one you're probably most used to seeing is in the lower left. That's a traditional hill shading from the northwest. And A and B, I think most of us would say is in a valley there, right? It's fairly easy to interpret. The sky model equivalent is on the right there. And then the lighting from the southwest is shown on the top. So these were the four tasks the users were asked to do: identify the valley and whether something was a valley or ridge, compare elevations, say if they were going uphill or downhill, or also associate a cross section with the terrain model. There were 352 participants, mostly bachelor students at the University of Warsaw, but also some faculty there. The male to female ratio shown. The average age was young, and some of that we looked into. So this would be, what we would typically expect for this. Just looking for a minute at just the Lambert, the traditional hill shading from northwest and southwest, and and people do much worse when the illumination is from the southwest. There's just that terrain reversal effect that's going on. But if we look at the sky models, both of the sky models do as well as the traditional hill shading from the northwest. So we don't have to worry about that the terrain reversal effect, at least as far as these tasks go, if we use the clear sky model. And this was true for all four of the different tasks that they did. They had no trouble with any one particular one of these tasks, kind of figuring out, from the clear sky illumination from the southeast, what the situation was. And once again, they were picking on a Likert scale, as is shown in the right of this slide. And, they were saying if they definitely believed it or maybe, so a little more uncertainty if they're saying maybe. And that was, the Lambert one was the one they were also least confident in, the Lambert from the southwest. There's a subtle difference there is a difference between the sky illumination from the northwest and the sky illumination from the southwest, but it's not as significant as the other difference. Response time, no difference for any of that. And the same with perceived level of difficulty. So they were, they might have been getting it wrong, but they were doing it fast, and they were, didn't think it was any harder than anything else they were doing. So that's kind of important too, right? Our maps are almost immediately giving an impression to the user about what these things look like, and that's the one chance we get. So just a couple of recommendations to use here. If you, hard to make that too strong a recommendation because I think almost everyone does that, right? Continue to not use southwest illumination with traditional hill shading, just because the people that look at that map are going to think your highs are lows and your lows are highs. It's just something that seems to be built into how we think about these things. Feel free to try, and they're going to be, once again, they're going to be confident in their interpretation, right? They're going to just think that's the way it looks. I have a visual model of what I'm seeing on that piece of paper, and that's how it looks. And then, feel free to experiment with these clear sky models. They seem to help people interpret where the highs and lows are, what is high and what is low, and it's not going to be more time-consuming or difficult for your map user to take a look at that and figure this all out. And if you're interested in playing with this stuff for yourself, the sample elevation models can be found at Tom's website. And Gene Trantham is the one that developed a lot of this clear sky modeling and other types of sky models out there. They're all available in a toolbox that actually works with ArcGIS Pro and QGIS if you're interested in doing some more advanced illumination effects on your terrain. All right, thank you.
Awesome. All right. And I think we have time for a couple questions. So does anybody have a question? Yes? Just shout it out. I'm not going to walk all the way over there.
I'm wondering if the issues of terrain misinterpretation still exist when people watch a model, or if it rotate, or if it's like animated or interactive.
Yeah, that's a good question. The question was, does this issue with terrain reversal still occur if it's an animated or dynamic map where you can rotate it around and look at it from different directions? And I'm not aware of any user studies that have been done on that at all. Yeah, sounds interesting.
Yes, in the back.
Do we know why people interpret it better from one direction and because it's a map?
Yeah, the question is, do we know why people interpret it as reversing if the lighting is from the wrong direction? People have ideas about that. You know, if something is hung on the wall, or if you're working at your desk, a lot of times the lighting is off to kind of that direction, you know, a little to one side and above you. And so it might have something to do with that, just how we expect the shadows to be cast or the shading to occur with that sort of orientation. But I think it's all conjecture. I don't know of any definitive statement on that.
Okay, we can do one more question, or not. All right, thanks so much, Patrick.
Thank you.